Sorry about that. Okay. Sorry about that. We can't see what you're writing. Oh, okay. So sorry. We're going to have to start over. I apologize. Yeah, that's what happens when. Anyway, I won't say. Okay, so here's. I apologize for Oscar and Blanca. You guys can't see anything. What I'm writing down here is the definition of what we call a sequence. It's an ordered, never ending list of real numbers. Okay, also called an infinite list because it never ends. And so you have A1, A2, A3, all the way up to what we call AN plus 1 with the three dots. So this is what you're seeing here is actually just a sequence in general by definition. Where A1 is the first term, A2 is the second term, and then go all the way down to AN. AN is the nth term, and then you have AN plus 1 was the n plus first term. And so this is what we call a sequence. All right, now we have alternate notation. So this is all kind of the notation you can see that mean the same thing. So sometimes they'll put, the starting point here. I'm going to try to find some colors. Start where you end. That means start at 1, and we do. Then go to 2 and go on forever. Sometimes they just keep that n out and they say start at 1, go on forever. This is a little subscript there. Sometimes they don't even write it at all. But we're going to really dive into the function notation version. So AN here, and I change this color. Okay, that's f of n, where n is a natural number. N is 1, 2, 3, and so on. That means the domain is just natural numbers. It's not real numbers anymore. It's natural numbers. So what we're doing here is we're going through really what a sequence is. And now we're just looking at examples where here they say start at 1, go on forever, and you're changing the n value. Okay, and then AN is just this function, 1 over n. And now here is this function here. So now you say, what if my function is 1 over 10 to the nth power? And now they want us to simply start at what? 0 for that n. We did. Then 1, and then 2, and so on. So we just simplify. The next term here will be 10 squared. 1 over 10 cubed, just change your n value, increase forever, and then you have another infinite sequence. But this is called, even though n is 0, this is called the first term of the sequence. This is the second term, this is the third term, and so on. So even though n starts at 0, n can start at 0. And in theory, it can start anywhere you want, but it doesn't typically. Typically it starts at n is 1 and can start at n is 0, but it's still called the first, second, third term. Okay, so anyway, just kind of let you guys know, we're looking at some very popular kind of series. And then I can say to you, here, let's generate the terms. And this is the next example. Right, so we start at 1, so this would be -1 to the 1, and then -1 what? Squared, -1 cubed, and so on. Okay, so what does this actually become? Do you guys know? What's -1 to the first power? What do you guys think? What's -1 to that first power? Isn't that just going to be what? That -1, and then -1 squared is what? +1, and then what else do you have? -1 cubed, isn't that what? -1 and +1. What do you guys notice about the pattern here? Anybody notice anything about this pattern? What is this? Yeah, this is what's called, this is alternating. So you guys know this is alternating in sign. Okay? Mean positive and negative. That's what they mean, alternating in sign. Okay. So I can say here, what about this sequence? 4. What does this mean? Well, all this is saying here, so if I really wanted to, maybe I'll do it, point out this detail. Right? Since we're just kind of getting introduced to these ideas here of a sequence. This is an. So an will be -1 to the n. And then over here, an is simply what? 4 is what we're saying. This is at an. This is called a constant sequence. So you say, what do you mean a constant sequence? Well, the first term is 4. The second term is 4. Third term is 4. That's a constant sequence. It's 4 forever. Because it's kind of like thinking if you look at function notation, that's a constant, if you guys remember. Right? Even though the domain is natural numbers. It's not all real numbers. So your first term is 4, second term is 4, so you can have a constant term. You know, you can have a lot of different things that you're going to see now. You might even see, and as an example, -1 to the n, let's say +1 over n. Okay, 1 to infinity. We'll see what that is, right? So just to kind of give you again, keep doing that. There's my an. -1, n plus 1 over n. So let's write this down. You say, well, what is this? Well, let's write down these terms. So what's the first term? Do you guys know? Just put a 1 for n. Okay, so for that first term, you just let n be what? 1. What's the next term? Now you let n be what? 2. Now you let n be 3, is that right? And that list goes on forever. But you say, what is this going to be? Well, that's -1 squared over 1. -1 cubed over 2. -1 to the 4th over 3. Pattern continues. So this is +1, -1/2, +1/3. The next will be -1/4, and you continue that pattern forever. So all you're doing is starting with 1, and then going to the next term and the next term, and you're generating the terms of the sequence. First term, second term, third term. Okay? So we're kind of getting to know some of these things here, some of these sequences here. Right? So you have another example. You might say, what about sine n pi over 2 now? Okay? Now, I'm going to leave off. I'm going to give you a little different notation here. See if you guys can figure that part out. Right? This portion, again, is the an. So an will be sine n pi over 2. And we're going to try to generate terms of the sequence. What's that going to be? You say this will be sine of n is 1 pi over 2. Sine of 2 pi over 2. N is 2. And what's this? 3 pi over 2. And then that list goes on forever. Okay, so do you guys happen to know what is sine of pi over 2? Isn't that 1? Okay, what's sine of pi? Good. What's sine of 3 pi over 2? -1. Okay, what do you think the terms are going to be? What would the next one be? Yeah, let me see what's going on. I need some space here. Oh, come on. Okay. Let's see what this is. Get some space here. So that's going to be 4 pi over 2 now, which is really what? 2 pi. And so yes, 0. And then the next term we can say, what is 5 pi over 2? Do you guys know? I think it's 1. Is that true? So what you're going to see is really this pattern continue. 1, 0, negative 1, 0, 1, 0, and so on. Okay, so this is just kind of defining that sequence. And then sometimes we have to explicitly be explicit about how we define sequences sometimes. And you might say, what do you mean? They might just use words and say a sequence of primes. So we have a sequence of primes here. And you might say, well, what's a prime? Well, what's the first smallest prime? Do you guys know? 2, and then what? 3, 5, 7, 11, 13, 17, 19, 23, and then that list goes on forever because there's infinitely many primes, ladies and gentlemen. That's a never-ending list. That list goes on forever. So you can have a list of primes. So they're going to describe it, and then you have the very famous Fibonacci sequence. That's so famous they even put its notation. That's a big FN, stands for the Fibonacci sequence. But they have to define it for you. This Fibonacci sequence is defined this way. They say, okay, F1 is 1. That's your first term. And F2 is also 1. And now they're going to give you a formula for this. How do you get the next term? Well, you simply add the prior terms. Fn minus 1, where n starts at 3. I think it starts at 3. First term, second term. Now it's the third term. Okay, so you have this very famous sequence that's done this way. First term is 1, second term is 1. What's the third term? You might say this is F3. And then this is F4, right? And this is F5. Well, what happens when n here is 3 now, right? I think it has to be 2, sorry. It has to start at 2 here. Apologize. So if n is 2, okay, let n be 2. Here's 2. Here's 2. Here's 2. What are they saying? What's the third term going to be? You guys know? They're saying the third term has to be F2 plus F1. So in other words, all they're saying with the Fibonacci sequence is add the 2 prior terms. So 1 plus 1 is going to give us what? 2. That's the next term. So you repeat the process. F4 is really just add the prior 2 terms. That's all they're saying. So F4 here is a sum of F3 plus F2, which means this will be 3. Similarly, F5 is F4 plus F3, so we're going to add the prior terms. This will be 5. And so, ladies and gentlemen, the very famous Fibonacci sequence you're looking at here, and we could generate this all day long. Okay, so here's our Fibonacci sequence. But they define it this way for us first. It's explicit. And, you know, your book has some other examples that they can kind of give you of a sequence anyway. And then you might say to me, okay, Mr. Judge, what's the deal with sequences, right? What do we care about in regards to sequences? Okay? So for any sequence, the reason we study them is because we care about something important. You know, why do we consider sequences, right? What's the big deal? Well, what we care about isn't where they start. We care about how do they end. So how do these sequences end? That's what we care about. We don't care about where they start. We care about where they what? End. So, you know, if you're going to get a tattoo about sequences, this is what you want to write down. Or at the end of the day, you may say to yourself, well, what's the big deal with these sequences? Well, we don't really care about where they start. We care about how they end. That's it. So there's two ways they can end. There's two endings. So I'm going to say this. I'm going to say we have two what? Endings. We can say they converge, or we can say what? They diverge, ladies and gentlemen. Okay? Because when I tell you, how do we care about these things? We care about what? How they end. Well, that's as n goes to what? Infinity. You guys with me on that? This is what we mean by that. What happens as n goes to infinity, because these are never-ending terms, right? Never-ending. It's an unending list of terms. So we care really how they end, not how they start, just how all of these things. We only care about how they end. That's it. So every sequence here has an ending, has a summary. You go, what do you mean? What's the summary? Either they're going to converge or they're going to what? Diverge. Now you might say, what does that even mean? Well, converging, we're going to write this way. We're going to talk about this notation. Okay, AN goes to L as N gets big. So some of you guys are going to like this because you've seen it already in Calculus 1, right? This is convergence, ladies and gentlemen. Calculus what? 1. Okay, do you guys know what we're talking about? Do you guys remember the topic in Calculus 1 was this? This was limits what? At infinity. Okay, you go, what do you mean? What's limits at infinity? Do you guys remember that? Limits at infinity in Calculus 1? So say Calculus 1 is back. In Calculus 1, you let the limit of a function. Right? Or it was the limit. Remember this? This is Calculus 1. So I'll just remind you guys. Calculus 1, you did this already. These were limits at infinity. But f, for your functions here, this was a real valued function. That means the domain, you guys had were real numbers. That's not happening now, though. Okay, so that's not really happening now. So let me guys remind you, Calculus 1, when you had limits at infinity, what was this all about? Do you guys remember? This is about what? Horizontal asymptotes. Is that true? So the nice thing about this class, even this topic, is you guys actually had, remember, L has to be finite. You guys remember that stuff? Remember this? This is from Calculus 1. And that's like the definition. Y equals L. That was your horizontal asymptote, right? This had to be a finite number. They gave you a horizontal asymptote. Let me draw a picture, if you guys remember now. Right? If you said, oh, is that this kind of topic? See if I can do it. Yeah. That's a bit better. Whatever. So this is a nice continuous function, ladies and gentlemen. You guys are looking at that. That's going to be f of x. And if you guys remembered, you know, this behavior here, this gave you your, this was y equals L. Remember that? This was your horizontal asymptote. You looked at the limit as x got big. That's calculus 1. Okay, do you guys remember all that stuff? Limits at infinity? Okay, well, now you might say, well, what is this? Well, an is fn, and what's the domain? You guys remember the domain we said? The domain now is going to be what? Natural numbers. So now you might say, well, what's the difference here? Remember, natural numbers is this set. 1, 2, 3, and forever. Okay? So now you might say, you might have something like this. This is really when n is 1, that's location, that's called A1. Remember, your domain is the input. Now, n is 2 here. Okay? This is A2. And that's your altitude, by the way. So this would be A1, right? This would be like A2, so you guys know. It's like your y value now. And then similarly, you have 3. And then what? 4. And then what? 5 and 6. And so on. Okay, so it'd be like A3. This would be like A4, A5, A6. These are all y values. A7. Okay, now what I want to share with you guys here, what it really means to have convergence. It's a very formal definition. To have convergence. Okay, so let me define it for you guys right in here. This is what you want to leave here today. Definition of convergence. Here's what we say. We say a sequence AN converges. Okay, let's see what that means. To a finite number L. Okay. Now you say, what are they talking about? Well, this limit equals L as n goes to infinity. This is what they're saying here, ladies and gentlemen. Okay, just like you have had before. Okay. We're going to give you guys the definition of convergence now. If for some term, some n, sufficiently large, so at some n value, right? This is my term. We don't know what that is. Well, for some n, any epsilon greater than 0, there is a natural number big N such that the absolute value of the difference is less than that epsilon. And that's for all n that was sufficiently large. Here's what we want to say. Just want to kind of emphasize a few things here. Any epsilon greater than 0, there is a n such that eventually this criteria is satisfied. This is a very formal definition. And I'm going to kind of express to you guys in terms of the picture what that means. And, you know, an epsilon is, so you guys know, positive. And typically, we think of that as a small positive number. But anyway, let's focus on the algebra, okay? We're going to focus on the algebra here. Here's what I mean by the algebra. Do you guys know what that is, actually? You know the definition of the absolute value less than some positive number is? That is equivalent to saying that the difference, this is an absolute value inequality, right? That portion right there. Okay, you guys remember absolute value inequality? And I'm going to add L to the middle, the right, and the left. So we end up with L minus epsilon less than AN less than L plus epsilon. And that's good for n greater than or equal to big N. So in other words, eventually, all they're saying is, eventually, all the terms of the sequence is going to satisfy this inequality. This, to me, is how I think of convergence, and I'll share with you graphically. This is how I think of it. This is what I mean by that. Okay, you got that L minus epsilon, that positive number, and then you got L plus epsilon, that upper value. So I'm just going to say, I'm going to emphasize that. This is a lower value, and this is an upper value. And this is what we mean by that. If we go to the picture, here's kind of what we're saying, ladies and gentlemen. What we're really saying is this, okay? For any epsilon, I'm going to define this E, epsilon, positive number. I think that's kind of not a good graphic, but I think this will be a better graphic. Okay, this is L plus epsilon. This is L minus the epsilon. I think we made that pink. And so this is what we call, I'm gonna do this all pink here. Okay. So this is around L. This is that convergent value L, right? Here's my L. L plus epsilon, L minus epsilon. So this is really what it means. What that means is there's going to come a point in time, some n, where every term of the sequence is in this epsilon neighborhood. Okay, you guys with me on that? There's going to come an n, in this case n is 2, where every term will be inside that epsilon neighborhood. How do they define it? L plus epsilon, L minus epsilon. Okay, you're in what's called an epsilon neighborhood. Every term of the sequence is in that neighborhood. This is what that means. Starting at, in this case, n is 2. Now, you know how they say this is for any epsilon, for any positive number? This is going to be the power of this, right? This is what I want you guys to understand. You could define any epsilon neighborhood. You can make a smaller epsilon neighborhood. Okay, so I'm going to erase this. and say to you guys, I could make an even smaller epsilon neighborhood. Where eventually every term will belong inside my what? Inside that neighborhood. Say, well, how small can you do it? Well, I could make epsilon so small, and I'll do it in pink. Okay. Well, let me do this. Let's take this highlighter that's already at 12. There we go. Yeah, maybe. Okay, it's smaller. Come on. Let's just try it now. I can make epsilon so small something like this, a smaller neighborhood. That'll be the L plus epsilon, L minus epsilon, where eventually every term is in that tunnel. So it could be like starting at 6 and forever. Okay, I can make that epsilon neighborhood so small that eventually every term starting at, some value will be inside that tunnel. That's all they're saying. It's a very, very powerful definition. This is the meaning of convergence here. That's why they say for any epsilon, eventually every term will be inside the tunnel, the epsilon neighborhood. So in pink here, you can think of this as a tunnel, ladies and gentlemen. And maybe I should make it just a little bit bigger so you guys can see that, yeah, eventually every term will be inside that tunnel around L. That's what they mean by this definition and the equivalent form right here. Eventually every term is between those numbers. Because here's my positive epsilon value. And here's my negative. I'm sorry, they're both positive. Epsilon's positive. Epsilon's always positive. That's the formal definition of what we call convergence. And of course, there we go. It's kind of weird. Okay. Now you might say, well, what's the other situation? What if you don't have that? What do you think we call it? Divergence. So what does divergence look like for us? Well, divergence looks like this. AN does not exist as n goes to infinity. Okay, AN does not exist, meaning this does not happen. You don't satisfy this definition. You don't satisfy that picture. So divergence, we're going to talk about this. That can mean a lot of things. I'm not going to say a lot of things. That can mean some things. Convergence means you go to a finite value. And it satisfies, L is finite. This does not exist. That means two things. Actually, it means three things. AN can go to positive infinity. AN could go to what? Negative infinity. Or AN just simply does not exist. There's really three flavors of does not exist. You're going to see that. It's essentially we can't create an epsilon neighborhood. So I want you guys to notice something here. Give you some very simple ideas. Right? give you an example. You guys see this sequence? This sequence converges. Just from the definition, right? You say AN is 1 over N. Well, what does that actually mean? You guys see this here? So if I were to say to you guys something like this, what are we really talking about? Just kind of drawing a picture for you. It's going to be hard to draw a picture. It's not going to be to scale. Like if this is 1, for example, and it's not to scale, so let me not do that. That's more like 1. See this here? What's going on with this particular term of this what? Right? How do I know about this term? Right? How do I know this behaves that way? Do you guys know A1 is 1? Is that true? What are the terms here? 1, 1/2, 1/3, 1/4, and so on. That goes on forever. Is that right? So what do you guys know? Where does this go to eventually? Go to 1/7. Aren't you getting closer and closer to what? 0? So, I mean, eventually around 0, if I do my little pink, eventually what's going to happen? You'll have that epsilon neighborhood around 0. Is that right? And eventually all the terms of this particular sequence is going to be around 0. So this is actually a picture that we say AN, which is 1 over N. That goes to 0 as the terms get big. Okay. So here's a very, very simple concept with that particular sequence. Let me give you, and this is what we mean by convergent, because this goes to a finite number, right? 0 is finite. Meaning it's not infinite. Compare that situation to what? So you guys can see this divergent situation very easily. Okay. So I'm going to say here's just N, very simple. Okay, just N, and now you might say, okay, what's AN? Right, AN is just N. Which means think of a function N, that's the domain. Right, like back up here, if you said to me, I want to think of f of x is what? 1 over x. Okay, if you guys remember, we're kind of, that's your function. F of x is 1 over x, part of it. But now, you might say, well, what am I thinking of now? Do you guys remember this function? Just f of x is x? We're not going to graph the real numbered version. We're just going to graph the domain here with natural numbers. So you might say, well, how does that kind of look? I'm going to try to do this here. Right? What do those terms look like? Well, you got 1, and then what? 1. And then you have 2, and then you have what? 2. 3, 3. 4, 4. This goes on what? 5. This goes up to what? 5. You guys okay with that? 1, 2, 3, 4, What's the deal with this? Can I define an epsilon neighborhood where every term belongs eventually? No, because even if I did an epsilon neighborhood, you said, what if you did an epsilon neighborhood around 3? Right? What's the problem with that? Every term of the sequence, if I try to define or create an epsilon neighborhood around 3, for example, try to make that, what's going on? We only have really what? One term in the tunnel. All the other terms are outside the tunnel. Is that right? That epsilon tunnel. Compared over here around 0, every term eventually is in the what? Tunnel around 0. Maybe you said, okay, then 3 maybe not, but every term starting at 4, then 5, and 6, 7, 8, 9, 10, and forever. Here, what's the problem? An epsilon could be any epsilon. You can make that smaller and smaller. So it does. So in other words, I can make epsilon so small that it just doesn't satisfy the neighborhood, right? Being in that epsilon neighborhood. You can't get every term in the tunnel. So even if I make epsilon smaller, because that's any epsilon could be a super small value. It's not going to be in the tunnel. So what do you think this means? It doesn't satisfy the definition. Therefore, it what? This what? Diverges. It does not converge. So this is a very simple picture. This converges. These are some very simple pictures of convergence and what? Divergence. Now, what if I say to you, here's another situation, right? See if you guys understand this. Remember this sequence here? What is this sequence? Do you guys remember? What sequence is that? Isn't that -1, +1, -1, +1, -1, and so on? Okay, you guys okay with that? So I'm going to take this to demonstrate to you this is another type of situation. See if you guys can tell me graphically. Okay, because that kind of idea I just gave you, the definition, is important here. Okay, so when n is 1, you already say, Mr. Judge, that's where maybe this is where -1 would be. Okay, now n is 2, +1. N is 3, you're back at -1. Is that right? N is 4, you're back at +1. N is 5, you're at -1. N is 6, you're where? At +1. So I'm actually looking at the term here, the terms of the sequence. Go back and think about this. Can I draw an epsilon neighborhood around a value where every term eventually is in that tunnel? What do you say, Mr. Judge, around 0? I'll say no, because any epsilon, remember this is the idea, any positive number, any positive epsilon. So if you create an epsilon neighborhood, none of the terms are in that tunnel. You guys okay with that? Because the terms are all outside the tunnel. Okay, what if I said to you, or you said to me, well, you know what we'll do then? Let's just move it up here, create our epsilon neighborhood around, 1. Now, is every term in that tunnel eventually? The answer is no. Why? Maybe you have only the even terms, right? Like when n is 2, when n is 4, when n is 6. What about these others? They're outside the what? The tunnel. And even if you said to me, well, then put it around -1. Don't put it around +1. Move this around -1. Well, all you did is make all the what? All the odd numbered terms inside the tunnel. You go, okay, this first term is there, third term, and the fifth term. But what do you guys notice? What is outside that tunnel? All the even terms are outside. So what's the problem? You could never get every term eventually in the tunnel. Is that right? So what do you think that means? Does that mean convergence? No. What does that mean? That's also an example of what? Divergence. So remember I gave you guys this idea. I said, you know what? I gave you divergence to mean does not exist. You already know about going to infinity and going to minus infinity as it does not exist. But remember I said there's a third version of does not exist? You just looked at it. So if you go to infinity as n gets big, that's a flavor of does not exist, meaning it's not finite. It needs to be finite too. They say exists and is finite. Sorry. Does not exist means you go to infinity. It means you go to minus infinity. It also means neither. It just simply means it does not converge. It means it doesn't satisfy the definition, the formal definition right here. Meaning you can't get every term eventually in a what? In a tunnel. Can't do it. It's just that simple. Okay, I'll say that again. Eventually, every term will belong inside this tunnel for any epsilon. Right? So you say, what are these? Here. Eventually, every term is in the tunnel. That's what that means to have convergence. If you can't do that for any epsilon, for a small epsilon, you have to shrink the epsilon over and over again. Eventually, all the terms will be in the tunnel. And if it can't be done, ladies and gentlemen, like in this case, it'll never be done. Here, it can't be done. Here, it can't be done. We say these two sequences what? Diverge. So I just want to share with you guys, in all honesty, the simplest examples of convergence and divergence of this definition I gave you. This is a very formal definition. This really is math right here. You know, so we really formally deal with mathematics. We deal with that definition. That's a very formal, that's a rigorous definition, ladies and gentlemen, of convergence for a sequence. Very rigorous. Okay, you guys okay with that? And I'm introducing that to you, and that's why they say sufficiently large for some n, every term satisfies this. This is really what it is. L minus epsilon is less than an, which is less than L plus epsilon. All they did was solve an absolute value inequality, and now they're saying every term eventually belongs in the tunnel. This is the tunnel format here. Okay? That's the equation for your tunnel. And this is for some n. This means eventually. So like I said, we only care about how our sequences end, not how they start. Do they end in a tunnel? If the answer is yes, we say it converges. Okay? If they end in a tunnel, I'll say it again, converges. If they end in a tunnel, convergence. If that never happens, diverges. That's simple. If it doesn't happen, diverges. You could go to infinity, it'll never happen. You could go to minus infinity, it'll never happen. It could be alternating, it'll never happen. Because we care about eventually, every term eventually needs to be in a what? In the tunnel. Around some finite value out. And that's what convergence means. Somebody have their hand out. Anybody have any questions? Yes? Yep. Exactly. Yep. Exactly that. That's the width right in here. This is going to be really this is L plus epsilon. This is L minus epsilon. Epsilon is thought of as being a small number. Like it could be 1/10. It could be even smaller. So, I mean, you make epsilon as small as possible. It could be 1/10. It could be epsilon could be 1 over 100, 1 over 1,000. Epsilon could be a super small number. Eventually, all the terms still will be in the sequence, will be in that tunnel. It's a very powerful idea. Make epsilon small as possible, and then eventually all the terms will be there. If all the terms are there, how it ends, you got convergence. Don't make epsilon large like 1,000. No, epsilon you can make smaller, smaller, and smaller, and eventually every term will be there. It may start at the 100th term or the 1,000th term, but if it's going to start there, because we only care about how it ends, that's fine. So this definition is extremely powerful. When I was a college student, it took me a while to really understand that definition. It took me a long time to understand that definition. And what I'm telling to you guys is essentially what it is. That for any, see that? For any epsilon, we could define a tunnel where eventually every term belongs in it. That's it. Just what I just told you guys, it took me a long time for that conclusion. For any epsilon, for any small positive number, we could define that tunnel where eventually every term is going to be inside the tunnel. Could be a super small tunnel, doesn't matter. Eventually, if all terms are in there, has to be all terms. That's what it means to converge around that value L. A picture is worth 1,000 what? Words. That's kind of the standard picture. If you guys want to look at any calculus book on convergence for sequences, they'll draw a picture like that. That's the picture. And it's the same picture for horizontal asymptote. Same exact picture. It's really the equivalent definition. Anyway, ladies and gentlemen, I just wanted to introduce this to you guys today because we're going to be working with all of these things here. Starting tomorrow, we'll be working with some limit laws, just like you guys had for Calculus 1. You can have limit laws here in Calculus 2 for limits at infinity, and it's going to be recognizable. Only the domain now is natural numbers. It's not real numbers. So we're going to be working with limits at infinity again. What do you guys think? Is that okay? All right. We'll see you guys tomorrow. Take care. Stay safe. Have a wonderful day. The idea here of sequences and convergence and divergence for sequences. Okay, it's a very simple but yet complicated in some way to start to get used to that formal definition. But it's a pretty simple idea. You just have to be within that epsilon neighborhood, that tunnel, forever, eventually, every term in the sequence, and that's what you're looking for now. So I'm going to kind of cut straight to the point with some of these things to share with you guys some facts here. Here's a fact regarding that convergent idea that I gave you guys. Okay? That if the limit of f of x equals L, and this is from Calculus 1, by the way. Okay, so it's from Calculus 1, and then they're going to say, and you're going to let an be f of n. You're changing the domain to natural numbers, okay? Then really the limit as n goes to infinity of an is L. So this is going to be an important fact that we use with limits, really. This is going to be our starting point. We're working with limits. Now, it's very simple in the sense that, remember this, okay? This is Calculus 1. This is n behavior. And let me be careful. That's not n, that's x. Okay? So that's Calculus 1. And L is supposed to be finite, by the way. Okay? That's something I really want to emphasize here. This number is finite. That is, again, that horizontal asymptote from Calc 1. Okay, so that's just n behavior limits at infinity from Calculus 1. That's all that is. Now what they're coming through is saying is, okay, we're talking about sequences now. And what you really care about is how they end, not how they start. How do they end? And now this is sequence notation. They change the domain. That's all that is. The domain is natural numbers. The natural numbers are starting at 1, 2, 3, and so on. So you went from a real numbered domain to a domain of natural numbers. And all they're saying now is, hey, guess what? The limit now as n goes to infinity for that an is the same L. So it's kind of just like a sleight of hand. It's just based on changing your domain to natural numbers. And that's how you start to get a handle on, you know, the idea of convergence. So this is what it means for convergence too. Now, if you don't have this, then you have divergence, really. So it's kind of like an else. Else, you have divergence. Else in programming. And, you know, so note, all they're saying is that limit now as n goes to infinity of an, which will be really the limit as n goes to infinity of fn, if this equals plus or minus infinity or simply does not exist, then that's the divergence that we're talking about. Okay, so you have two things, convergence and divergence. So here's kind of where we're at. And what this does then, it brings up the idea of limit laws. Because we had limit laws before for functions, we have limit laws now for sequences. And how they start the limit laws is they'll say, okay, you have an, here's one sequence, here's another sequence, c is a constant, for your limit laws. In question 1 limit law is the limit of a sum. So the limit of a sum is sum of limits. And I believe they want these to converge, but okay. Yeah, these are convergent. So the limit of a sum is sum of a limit. Just like before with functions. Limit of a difference is difference of limits. Just like with functions. Then you have the limit of a constant times a function. You can pull out the constant. It's all just like with functions. And then here, the limit of a constant is just a constant. Limit of a product is product of limits. And then limit of a quotient is quotient of limits. So all of those properties we're going to use just like before. So all I'm doing is doing the same thing that we had in Calculus 1 with some of these limit properties. You can't divide by 0. Okay, so they're going to say if the limit of Bn is not 0. In fact, none of the terms can be 0 for Bn. because you just simply can't divide by 0. And then 7, limit of an to the p power is limit an to the p power, and that is if p is positive and an is positive. We're not talking about complex numbers. And we'll see some examples, I guess. And we're going to kind of save some of these things here, I think. So we want to try to talk about some examples. Yeah, we're going to talk about some examples. So if they want you to have the limit now as n goes to infinity, you have n plus 2 over n. Okay, you just kind of use some limit law, use the limit laws that you guys have had. So by limit laws, I would say to you, notice doing some algebra here. That's n over n plus 2 over n, right? Which is the limit of 1 plus 2 over n. So if you use the limit laws, you got the limit of a sum. That's what they're saying. And then I could pull out this constant here. So I have the limit of 1 plus 2 times the limit here. 1 over n. Now, this is what you see with the first kind of example. So you might say, what's the limit of a constant? Well, a limit of a constant is the what? It's the constant, 1. And then this is 2 times the limit of, so this limit, what I'm going to say to you guys, where does this limit go? Do you guys know where that limit goes? Why does that go to 0? Because what this statement is saying to you here, right? We started the day with this statement here, this fact. We're really using this fact. Okay, you might say, what do you mean we're really using that fact? We're using this fact. Here's what I mean by that. That this is the limit. If you go back to now the variable x, right? Wasn't that limit equal to 0? If x was a real number, that limit was 0. Is that right? So that means if you change the domain from not any real value but to natural numbers, it's the same conclusion. That's what they're saying. So yes, that's 0. And then this is like a constant function. So that'll be 2 times 0. So the final answer here is going to be simply what? 1. And that should make sense because this function here, x plus 2 over x, that limit goes to 1 here. Okay, so that's your first example using limit laws and using that fact we started with here. Just using all these laws here. They're just saying, consider your function to be that of natural numbers, an. So, I mean, you could, if you said, can I just call this portion here the an? It's the same thing. An, is fn. That's really what you're looking at. So you change the domain of the function. That's it, to be natural numbers. And you have the same following limit laws. So it's kind of interesting. If I go to Desmos, I wonder if it'll do that. It doesn't. It doesn't. I thought it would draw those points there, but it doesn't. It's like X. So as you guys can see, this limit's going to go to 1. Well, you can't see it, but anyway. This limit is 1. It has a horizontal asymptote at 1. If it were a function, if this were calculus 1. So if this question was a calculus 1 question, you have a horizontal asymptote, you know, but it's not. This is just a regular sequence. So what this means is, you know, this sequence, n plus 2 over n, this converges. And it converges to the finite value 1. So that's kind of the first example. Where does that sequence converge to? So you're showing that it converges to 1. Okay, isn't that pretty simple? It's going back to really calculus 1. So they can give you a sequence here like this. Maybe e to the minus n. And they can ask, does this converge or diverge? So this is the an here, right? So you can say, are they telling me that an is at e to the minus n, which is your f of n as well? It is. So you're going to look now at the limit of that f of n as n goes to infinity, which is the limit of 1 over e to the n, right? So where does this go? You guys know? What do you guys know about this? Yeah, that goes to 0. Is that right? This limit goes to 0. So that means, and that's 0 is finite. So it converges to 0. So in terms of notation, you might write e to the minus n goes to 0 as n gets big. So those terms of this sequence here, if you looked at this, you might say, is that e to the minus 1, e to the minus 2, e to the minus 3, and so on, right? So this sequence eventually goes to 0 as n gets big. Like I said, we only care about where it ends. We don't really care about how it starts, just where it ends. So this is the n behavior in some sense, right? Because that's what's happening. N is getting big. So the terms of the sequence goes to 0. You know, like this one here, if you looked at the terms of this sequence, we said, what do the terms of this sequence look like? Well, you can look at the terms here for this one. Start at 1. Looks like it's 3 over 1, and then 2, 4 over 2, n is 1, n is 2, n is 3, 5 over 3, n is 4, 6 over 4, and so on. And yes, you can simplify the fractions. 3, 2, 5 thirds, 3 halves, all those terms eventually go to 1. We've shown that these terms go to 1. So we're looking at the terms here of this sequence here. 3, 2, 5 thirds, 3 halves, and then the next will be 7 thirds, I guess. 8 fourths, which is am I doing it right? 3, 4, 5, 6, 7. No, 7 fifths. Anyway, that's fine. So we have to show that it converges or it diverges. Similarly, limit e to the n over n. N gets big. In other words, they're asking us to look at where, if I write it first as a sequence, right? What does that look like? E to the 1 over 1, e squared over 2, e cubed over 3, e to the 4th over 4, and that goes on forever. E squared over 2, e cubed over 3, e to the 4th over 4. We have to see where this converges or diverges. Well, this one, you'd say, okay, let's look at the limit of e to the n over n. And it might be that you're going to have to look at the limit as x goes to infinity, e to the x over x. So you're going to have to go out to this. You say, why? Well, because this is infinity over infinity. Is that right? So we're looking at the terms of the sequence. We can't say anything about that. Now, have you guys ever studied this before? What do you guys think is back? L'Hopital's rule. L'Hopital's rule. So this is the derivative of e to the x, which is e to the x. The derivative of x, which is 1. So now you have that limit x goes to infinity, e to the x. What is this? Infinity, ladies and gentlemen. So that means that this is also what? Infinity. Okay? So you had to change. Now, I have to say this to you guys, that, give you the disclaimer that you have to go out to the variable x, because L'Hopital's rule is defined really for x being a real number. So that's why you had to look at this limit in terms of x, and you'll see that in your book. They go, why do you have to do that? Because L'Hopital's rule applies only for values of x being real numbers. The assumption is over, x over that interval. And so if you change the domain to be just natural numbers, then you really technically can't use it. So you just say, okay, I'm going to go back and use my L'Hopital's rule in terms of the variable x. Now I get an answer in terms of x, but then that means now if my domain is natural numbers, it's the same answer. This is code for saying that this actually what? Diverges. That's what you want to know. So you're showing that the terms of this diverge. In fact, they get bigger, bigger, and bigger. Right? And so if I go to Desmos, and if I say to you, look at the curve. You'll say, yes, the terms get what? As x gets big, what happens with that curve? Doesn't that go up forever? Okay, so the terms are going to go up forever there, just going to the real number there. So this is an example of how you use limits to show convergence and divergence. Give you guys this example here. They give you n plus 1 over 3n plus 1. Okay. So here is the sequence. And so if you plug in, if you start to look at the terms, looks like that's 2 over 4 for the first term. Now n is 2. 3 over 7. That now n is 3. 4 over 10. Now n is 1, 2, 3, 4. 5 over 13. You know. We want to know, because remember, this is, you say, how am I generating this? Right? This happens when n is 1, when n is 2. That's the second term. Here's my third term. We don't care about how it starts. We care about how it ends, what's happening with the end behavior. So we're going to look at this limit now as n goes to infinity of n plus 1 over that 3n plus 1 using these limit laws. Now, you might say, oh, Mr. Judge, I'm going to apply my what happens as n gets big, you're going to say, I get that infinity over infinity, so I'm going to have to go to calculus 1 or calculus 2, right? You could use calculus 1 or calculus 2, actually, on this one. Right? You say, isn't that infinity over infinity? It is. But by L'Hopital's rule now, the limit as x goes to infinity is going to be what? 1 over 3, which is 1/3. You know, so that's finite. So this also is what? 1/3. You know, so that one's 1/3 as well. Okay, what do you guys think? Is that kind of simple? Let's start to kick some of these up a little bit. What if they give you the square root of n over 1 plus the square root of n? Okay, so this is an now. And I'm going to try to change notation. We want to see where an goes to as n goes to infinity. I'm just going to look at this in terms of notation now. Now, you might use L'Hopital's rule again if you guys wanted to. But I'm going to try to do this from calculus 1. Okay? So what I'm going to do now here is this. I'm going to say, I'm going to divide every term by the variable to the highest power. So I'm going to take that square root of n, divide by the square root of n. 1 over the square root of n plus the square root of n over square root of n. This is a calculus 1 approach, if you guys remember. It's kind of calculus 1-ish. Right? So you're going to get 1 over the square root of n plus 1 now. So what do you guys know about limit laws? What's going to happen with limit laws? This down here is going to go, this is going to go to what? 0, is that right? So that goes to 0. So you have 1 over really 0 plus 1, which is 1. So we didn't have to go out really to change the variable to x. We found that this is finite. So that equals 1 here. So we have convergence. So this converges to 1. So all those terms of the sequence, gets close to 1. Okay, give you another example. So let's change something just small about this. Okay, so if we change this one here, there's my AN again. We want to see where does this converge to as n gets big. Okay, so if I take the same approach now, n over 1 plus the square root of n. We're going to use the same calculus 1-ish approach and limit laws. Okay, divide every term by the variable to the highest power in the denominator. So you get n over square root of n, 1 over the square root of n plus square root of n over square root of n. We're going to take the calculus 1-ish approach and use limit laws. Okay, and then you say, well, what happens here? Well, it looks like the limit now is going to be square root of n, 1 over the square root of n plus 1 here. So what's going on now, ladies and gentlemen? This portion's going to go, this is going to go to 0. Is that right? And this portion's going where? To infinity. So you say, is this infinity over the 0 plus 1? That's really that's going to be what? Infinity. So what we're really saying is this, just so you guys really want to be very clear with. As n gets big, my numerator gets big, but the denominator goes to 1. So that ratio goes to what? Infinity. Okay, so I want you guys to see it this way instead. The numerator, as n gets big, my numerator is getting big, but the denominator is going to 1. So the ratio is getting big. This is divergence. Okay, so this is what we mean by divergence. So this sequence diverges. So this goes to infinity, this diverges. And that's what we're looking at. So this is a divergence sequence, and this was a convergence sequence, converges to 1. Yeah.
Why before when you not change it onto the x?
You could if you wanted. You could if you wanted. And then you might use even L'Hopital's rule, but we're trying to use here adapt to the what? The limit law properties here. That's all. You know, and then as some examples here, they might give it to you this way. They may say, okay, cosine 2 over n, notation-wise. You're trying to find convergence or divergence. And remember, this is going to be like, if you look at the first term, cosine 2 over 2. Now, if we look at the terms, just to kind of see what that is, that's like 2 over 1, 2 over 2, cosine 2 over 3, and then that goes on forever, right? So just kind of looking at the terms so that people can get used of this. Cosine squared, or cosine of 2, cosine of 1. This is radian measure, by the way. Okay, it's not degree. So they're going to look at this particular sequence. Just do one more. That's 1/2. It's 2 over 4. 2 over 4 is 1/2, by the way. So what happens here? Okay. So if you looked at the limit now, as n goes to infinity, cosine 2 over n, here's how you guys can look at this. What's happening here, if I said to you, as n gets big, what do you guys know about 2 over n? That goes to 0, is that right? Then that means cosine of 2 over n goes to cosine of 0. Now, maybe you want to go to x here. And because we didn't write down a limit law property for a composition of functions, right? So we don't have a limit law there for the composition of functions, and you're using continuity for cosine. So, you know, you might say as x gets big, 2 over x goes to 0. Cosine's continuous. So cosine of 2 over x goes to cosine of 0, and this thing equals what? 1. So what you're showing here is this limit here is 1. And that means this limit is also equal to what? 1. Okay, so this converges to 1. I guess we'll just highlight converges. So here, I'm going to give you guys some few examples to kind of get used to this. Here's a sequence. So we got inverse tangent of 2, inverse tangent of 4, inverse tangent of 6. That goes on forever now. The terms here. So here's my AN. So if you're going to look at this limit, what do you think's happening here, right? as n gets big, what do you guys know about 2n? Isn't that getting big? So where does inverse tangent go to? Is that pi over 2? And pi over 2 is finite. So this is a finite value. So this converges. And then we'll look at this here. So you got natural log. If we plug in 1 here, get natural log 1 over natural log 2, which is 0, by the way. Natural log 2 over natural log of 4. Natural log 3 over natural log 6. So if you look at these terms of this sequence. So we got our an again. Okay, so an here is natural log of n over natural log 2n. So if you wanted to see the limit here, right? You might say, is that infinity over infinity, and therefore go out to what? Your variable x, to use L'Hopital's rule? So by L'Hopital's rule, isn't that 1 over x over what? 1 over 2x times 2? Is that right? Don't you have to use a chain rule, right? And you say that's really the natural log of 1, which is 1. So this limit is 1 as well. So if you want, with notation, we can say this goes to 1 as n gets big, which means you have convergence because 1 is finite. Now, I want to give you guys this fact here. We have a fact to consider. And we're going to prove this fact later. Right? So here's the fact. If your limit of a sequence in absolute value, okay, so you take a sequence, you take the absolute value, and if you show that that equals 0, then you have the following statement. We'll prove that later. then the limit of the sequence is actually 0. Okay, so we're gonna see the proof of this later. Okay, so we're going to see this proof later. Now you might say, well, why do we care about this particular fact? Well, for example, here's kind of a classic example. I'm going to show this thing converges. Okay, so you can say, well, what do I do? Well, we take the absolute value of AN, because this whole thing is AN. Okay, you're going to take the absolute value. Now, you're going to use kind of some algebra, just so you guys know. You're going to get used to this algebra. Do you guys remember some properties of absolute value? What are some properties? You have the absolute value of the quotient. Isn't that quotient of absolute value? Okay, you guys know what I'm saying? Here's some properties. I'll do what I do with the trig class. This is the absolute value of A over B. Absolute value of A, absolute value of B. And then you got this product rule as well. So on top over here, this is -1 times -1 times -1. How many of these? You got very many. Over what? The absolute value of N. This is where you're using the product rule on top in the numerator. Okay, so this is like saying you have the absolute value of -1 now to the nth power, which is going to be, and that's over n. Do you guys know why that's over just an n? You know, just to kind of express to you, you got n of these here. This is 1, and this is n. So we're saying that this is really 1 over n. Why is that? Why do I get rid of the absolute value down here? What do you guys know about n? Right? This is what I'm saying. What do you guys know about this n? It's a natural number. Good. N is a natural number, so it's positive. You could get rid of that. It's never 0. N is 1, 2, 3, and so on. So what I'm saying to you guys here is this. What you should see in this example is the absolute value of AN is 1 over n. So the limit now of that is the same as the limit of 1 over n. And where does that equal? 0. So if you can ever show that the limit in absolute value of a sequence is 0, then that implies the limit of AN is 0. So this is the fact that they gave you, and they say we'll prove this later. Okay? So what you ended up showing here by that fact is that this goes to 0. So in conclusion, that -1 to the n over n goes to 0 as n gets big. This is really the conclusion of what you're looking at. So we showed that it what? We show that this thing converges. This is a very powerful fact that we're going to start to use with some of these examples. Okay, you guys okay with that? With this fact here, we're gonna prove it later though. So don't look at it and go, "Oh my God, I want to see the proof." We'll see the proof, but we want to do some more. We want to use this first. So for example, you got a couple of nice examples of this. Right, your book might have, okay, we let a n be -1 to the n to the third power over n cubed plus 2n squared plus 1. Okay, now I'm gonna share with you guys a little secret here. The second you see this, what is that? Do you guys know what that is? -1 to the n? That's what I call an alternating mechanism. It alternates your sign with plus or minus. The second you see an alternating mechanism, go over to what? The absolute value of an, which is going to be what you guys see here. Now, by properties of absolute value, like we showed earlier, you say, what's going to happen by properties of absolute value? I'll give you guys a few seconds to try this out. I'll be right back, though. Let me go get something. Give you guys some time to try this yourself. A few minutes. All right, take a look at this. Tell me if you guys see this idea here. I think this is an extremely important idea. Sorry, let's get that out. There we go. Can I write this way? Absolute value of -1 to the n. Can I use the product rule? You guys know what I'm saying? I'm using the product rule here. And we know this is going to equal now 1 here. So this is 1. Is that true? Right? You guys know what I'm saying? And you say, but then you have just absolute value n cubed over n cubed plus 2n squared plus 1 in the absolute value. Now, why can I get rid of the absolute value here? Do you guys know, isn't what you have inside here strictly positive? Everything here inside is positive. Everything. So that means I could get rid of my absolute value. Okay, so now all along we're saying this, that this is the absolute value of an. And so if I take the limit now, that's the limit as n goes to infinity of what? N cubed plus 2n squared plus 1. And what do you guys know about this limit? I can evaluate this from Calculus 1 rules. Right? Divide everything by what? By n cubed. Okay. So that's the limit of 1 over 1 plus 2 over n, 1 over n cubed. What does that go to? This limit is what? 0. Oh, I'm sorry. This limit is, what's this limit? It's 1. Is that right? It's not 0. That's what? 1. So then what does this mean? Okay, that's 1. So let's go back to the statement I gave you guys. What we said, if the limit in absolute value is 0, then the limit of an equals 0. I cannot use this statement, can I? Can't use it. So, can't use it, but I'm gonna ask you guys something here. I want you guys to note something. This is just as important. You see what we just showed? We just showed that the absolute value of an goes to 1 as n goes to infinity. You know what that means? This is an important detail. So I want you guys to note. I'm trying to figure out what color to write this here. Let's note something here. If you have the absolute value of n go to, well, here's what this means. Let's note what that means. This means that without the absolute value, an is going to alternate between plus or minus 1 as n goes to infinity. When you took the absolute value, you're saying to me, make every term here, make every term positive. See, an is not positive. Some values are positive, some values are negative. It alternates. Because if n is 1, it's -1. N is 2, +1. N is 3, -1. You have this alternating mechanism. And so by taking the absolute value, you're essentially making that term positive. Is that right? So without the absolute value, as n goes to infinity, an goes to plus or minus 1. So here's what I'm asking. What does this mean? It means something. It's, huh? Yeah. It means this limit does not exist. Because you're going to two values. You're alternating between positive 1 and negative 1. So if your limit does not exist, this is the idea. What does it mean about an? It means an diverges. This, ladies and gentlemen, is an extremely important detail. It's a flavor of divergence. You can't go to two values. You can't go to alternating values of terms of a sequence as it ends. So as the sequence ends, you alternate between positive 1 and negative 1. There's two limits, not one. It's alternating between plus and minus 1. Anyway, I just wanted to share that with you guys and give you guys another kind of example. The last one that's very similar. N cosine n pi. This is a similar thing because you might say, why? What do you guys notice about cosine n pi? This is an alternating mechanism as well. Right? What happens when n is 1? What's cosine pi? Negative 1. When n is 2, what's that? Cosine 2 pi, what's that? 1. When n is 3, cosine 3 pi, negative 1. That's the equivalent to this alternating mechanism. So cosine n pi is an alternating mechanism. So if I said to you, the second you see that, you got this statement now. Take the absolute value of that alternating sequence and see what you get. This is 1 really times n, which is just n. Because the absolute value of negative 1 to the n is just 1, and then 1 times n is n. So now you say, what's happening with this? Well, this thing goes to infinity as n gets big. That's not 0 again. So just by making all the terms positive there, it goes to infinity. So what that means is a to the n goes to plus and minus what? Infinity as n gets big. So you're alternating between positive and negative infinity. What does that mean, ladies and gentlemen? This means what? Diverges. Because the limit goes to two places. That's plus or minus infinity. That's a flavor of divergence again. So this sequence what? Diverges, and this is the whole reason. So this is an extremely useful fact and information that just doesn't center around the limit going to 0. If it doesn't go to 0, then it's divergent. Because you're looking at the absolute value of it not going to 0. That means it's going to two places. Yeah, I wish this had I'm kind of wondering if Desmos does sequences. I'm going to Google that. Say Desmos. Does Desmos graph sequences? I would love to see it. Yeah, you know what it does? Interesting. You want to see how Desmos does it? Let's try that out. How does Desmos do a subscript? Like if I said, okay, here's my A, where's the subscript at? I don't see subscript. Can I just say AN? Oh, here we go. A and there it is. I think I have to come out equals, what was the last one? Cosine n pi, it was n, cosine n pi. N, let's see. Cosine n pi. Okay. And then I think I have to put parentheses here. Big N. Comma. A sub A of N. So I'm going to say now A, where are you, A? I did everything that it showed me here, I think. Oh, no, this here is not a subscript. Okay. I'm going to have to go delete that. A of N. Come on, go all the way. Well, anyway, here's kind of, it's not graphing dots. I'll try to figure out how, too many variables. Try defining N. What do you mean? You guys know what N is. And A of N. I don't know. That's what it has. Let's see. We have plotted a point, however, by improving the list N, we have induced Desmos into plotting each point N, A, N, and the sequence from N is 1 to 100. Yeah, maybe there's more to it. So what I want to share with you guys is this, right? If you guys can see that in Desmos, let me share with you guys. That's N cosine n pi. So that's actually really X cosine X pi. So if you look at the natural numbers as a domain, you restrict the domain. It's alternating between plus or minus infinity. In other words, it's going up forever. That's why the limit does not exist. And that's what we just showed right here, really. Okay, so if you made the absolute value of it, just N, you know, we're showing that that limit does not exist. I'm going to try to figure out in Desmos if I just want to plot points. I don't want to plot the continuous function, X. So what I did also, too, in Canvas, assignment 4, I have you guys starting to get started on some of those things. This is under homework 4, I think. Yeah. So we're going to start to do some of those in 12.1. We're going to continue more tomorrow because there's more information in this section. This is a long section. The first section always introduces a lot of the main ideas. So I have to talk about tomorrow some other ideas like squeeze theorem, very minor, and what bounded sequences are, and so on, and the monotone sequence theorem, and then that's that. So there's another way of looking at this too. So anyway, I hope you guys enjoyed the lecture on how to look at convergence and divergence, and we'll see tomorrow some more of these ideas. So, okay, we'll see you guys later. Some more sequence lecture, because this is a pretty involved thing. Okay, so we did something yesterday that was pretty good, pretty powerful. So I want to tell you guys today, we got to give you some more information. Theorem. This is what we've also been using here. Another theorem. If you have the limit of an as n goes to infinity, right, and that equals, I would say L. So we've been actually looking at these kind of things, but I didn't mention this to you yet, and I should have. Okay? Remember, this an is really Fn. So if you have a finite answer, this is L. And that's finite. Then the limit of, well, they did this here. They do it this way. Let me get rid of this here. This is a different F. If I could get the eraser here, this is going to be a different F, okay? And F is continuous at A. So it's a different F. You guys already know, I always talk about that. And F is continuous at A. Then the limit of F of an equals F of A. And we've actually seen an example of that already. Okay, so we've kind of seen an example. Something's kind of simple if you want to think of it this way. Let's say an equals maybe cosine of 1 over n. Okay. So you might say, what are the terms of this? What are the terms here? Right? I'm just going to deal with some notation here for you guys. So you got cosine 1 over n. Remember, what does that look like for us? Start with n as 1, n as 2, and so on. So you can say this is cosine of 1, and then cosine of what? 1/2, and then cosine of 1/3, and so on. Okay. Now, I have to be very careful here, because again, it's all about notation here. And I'm going to do it this way. I'm not going to define it as an. You're going to see why I want to do it this way. You're going to define it as bn, ladies and gentlemen. Okay. In this theorem, this is your an in that theorem. Okay, so this is kind of what that means here. Right? So what do you guys know if I said to you guys, I change this on you so that we can use the theorem here? That's an. And what they're saying in the assumption, okay, is that an goes to what? L, as n gets big. That's the assumption. You got convergence of an being finite. Okay. Now you say, and then you also have a continuous function f. So what they're saying here is that an is going to be that 1 over n. And what do you know? What does that go to? Doesn't that go to 0 as n goes to infinity? Okay, you guys with me on that? That goes to 0 as n goes to infinity. So your function is continuous here. And it's continuous at 0. So your function's continuous at 0, ladies and gentlemen. So what that means is something very, very simple. What that means is cosine now of an, which is 1 over n, goes to cosine of 0, which is what number? Which is 1. So this portion right in here, this an here, right? That goes to 0, which means this goes to cosine of 0. Because cosine's a nice continuous function. And that's equal to 1. So what we've just shown is that this particular sequence goes to 1 as n goes to infinity. In other words, you have convergence. Okay, so you got this convergence. That's kind of an illustration of this portion here. It's an extremely important idea. So we actually kind of seen that if we looked at this from a calculus 1 perspective and you change the variable to x, it's the same argument that's used in calculus 1. Okay, but this time they're saying, and maybe I want to do it with the right colors, and sorry about that. I just changed even the colors on you. Okay, that's an illustration of that theorem. It's a very amazing theorem. And there could be a lot of examples of something like that. They can give you another example of this. They can say, okay, let this be e to maybe 1 over n squared. Okay, so this is going to be, now, let's look at the terms, right? Let's look at the terms of this. E to the 1 over 1 squared, 1 over 2 squared, 1 over 3 squared. Okay, you guys okay with that? So it's like e to the 1, e to the 1/4, e to the 1/9. These are the terms. Okay. Does this converge or diverge? Because that's really what they want to know. They want you to show it converges or show that it what? Diverges. Okay, you guys okay with that one? So you might say, I don't know where this goes to. Well, here's the thing about it. You can look at it this way. You can notice that the following here, right? We know if we take 1 over n squared, that goes to 0 as n gets big. Okay, so we're looking at this portion here. That's the an in this particular theorem, right? That's the an they're talking about. And that goes to a finite number 0. So you know something about the exponential function. So if we said, okay, what is this? This is, well, we say f of x is e to the x. This is nice and continuous at 0. So what you're now able to do is to say what? E to the 1 over n squared will go to e to the 0. Because that function they gave you is nice and continuous. It's continuous at 0. There's e, and this is what they're saying. That's what this theorem is saying. And so what is e to the 0? Isn't that 1? So e to the 0 is 1. So you're showing that 1 over n squared goes to 1, which is convergent. So this series converges. So all these values we're talking about, they get close to 1. You know, at the very end. Because remember, sequences, you don't care about how they start. You only care about how they end. And in Desmos, just kind of look at that one. We'll look at the function. Y equals e. And that's e raised to the what? 1 divided by, I guess, x squared. Who knows? So as you guys can see, that kind of, I didn't do the sequence. I looked at the function. Anyway, it's 1 over x squared. It's getting close to 1 in Desmos. So that's just an illustration of this theorem. It's in our book. Okay, and so the next theorem that we have to talk about, which is good, is also famous. This is the famous squeeze theorem. It's your famous squeeze theorem. Okay, so now they're going to give you 3 sequences. You say AN, BN, CN are sequences such that we know AN is less than or equal to BN, which is less than or equal to CN for all N. So all they're saying here is this. You have this AN here. And then you have this what? CN. This BN. This here is the smaller sequence. This is smaller. This is what? Larger. And this is in the middle. Okay, so that's not all. You also have the limit of AN is the same as the limit of CN. So it's the limit of the smaller sequence is the same as the limit of the larger sequence, which equals out. Then that forces the limit of the middle sequence to also be L. And this is called the squeeze theorem. Where L is finite. Okay, so it's a finite kind of sequence. Okay, do you guys remember the squeeze theorem from Calculus 1? We had the squeeze theorem from Calculus 1 as well. It's the same thing, but with functions. But now, but now we're looking at sequences where the domain is just natural numbers. So let's make sure we have all the details here. It's exactly the same from Calculus 1. Okay, so let's see the example here. So it's just like from Calculus 1, that squeeze theorem. So they're going to say, show the sequence AN, which is cosine N over N. Show this sequence converges to 0 or converges. Sometimes the book will ask this question here. They want you to show that that limit equals 0. So I think that's the kind of the real question. I can word it the same way, converges to 0. All right, you guys okay with that one? So let's kind of take a look at this one here. You say, well, how do we do that? Well, this is a very famous example of using squeeze theorem. Okay, so let me give you guys the argument about it. This is kind of what they want you to do. Do you guys know anything about the cosine of a function? Cosine lives between -1 and +1, right? So this is what we know is true for all n. For every natural number, because it's true for every real number, right? Because you go, wait a minute, it's true for every real number. It's true for every natural number. You guys know. Now, do you guys remember what you can do for any inequality? If you divide the left, the middle, and the right, it doesn't change the direction because n is greater than 0. N is positive because you're talking natural numbers, right? N is a natural number. Natural numbers are 1, 2, 3, and so on. So what you're really looking at is the following here. -1/n is less than or equal to cosine over n, cosine of n over n, which is less than or equal to 1/n. Now, ladies and gentlemen, you got these values here. Here's my point. This is what? This is the smaller sequence. And this is the what? Larger sequence. And what do you guys know? That the limit of that larger sequence as n goes to infinity is 0. The limit of the smaller sequence, if I factor out the -1 by properties of limits, is also 0, right? Because this is -1 here times that limit of 1/n, right? So -1 times 0, you already know that, is going to be 0. So you're showing that the limit of the smaller sequence equals the limit of the larger sequence. They're both 0. So here's what you must say. You have to cite it. By the squeeze theorem, that now implies or guarantees that the limit n goes to infinity, cosine n over n is also 0. And that's what you're trying to show, the middle sequence, right? So the middle sequence as well is 0. That's what we're showing. And that's, of course, by the squeeze theorem. So, you know, there's more properties there for us to look at. And there's nothing, I should say, as another example, a very simple example, they can also say show the limit n goes to infinity of sine maybe of 2n over n squared is also 0. Okay, this is, again, this is the an. Or not an, this is going to be your sequence. Right? They're looking at this sequence here. They're saying sine 2n over n squared. That's the sequence they're talking about. So it's very similar to what you already did, because you say, isn't it true that the absolute value now of sine of really any angle, okay, is less than or equal to 1, which is saying the following. Okay, so what that means is that sine of 2n for all n. Theta is in radians. Theta is a real number. Okay, so you guys know theta is a real number. It's a radian measure. So it's another way of saying real number. All right. So again, from that relationship, we can divide, I'll use red again. From that relationship, we can divide what? The left by n squared, the middle by n squared, and the right by n squared. And what do you end up with? Negative 1 over n squared is less than or equal to sine of 2n over n squared. Over n squared, and that's for all n. Okay, so I want you guys to see here really easily, smaller sequence, and then you have the what? Larger sequence, and this is the middle sequence. You got the middle sequence. So what do you guys know about this, right? You know what? That the limit of 1 over n squared is as n goes to infinity. What's this equal to? Isn't that 0? And you also know the limit of negative 1 over n squared. Pull out the negative sign. That'll be negative 1 times 0, which is also what? 0. So you're showing now again that the limit of the smaller sequence is what? 0, and the limit of the larger sequence is also 0. So we can now say again by squeeze theorem, the middle sequence is also 0. So the limit as n goes to infinity now of that middle sine 2n over n squared is also 0. And that's by the squeeze theorem. So this is kind of the illustration of why they want you to use squeeze theorem. Okay, you guys okay with that one? Anyway, all this work with sequences. Now, here's the next question here. And they show that for positive a values, the limit as n goes to infinity of the nth root of a equals 1. And I guess I want you to show that. just looking at a few things here. Okay, yeah. All right, ladies and gentlemen. Okay, let's take a look at this. So you might say, what does this mean here? Well, we got to look at what this is, right? What is this? Do you guys know what that is, algebraically speaking? Yeah. It's a to the 1 over n. Okay, so what I can suggest you guys, this is using some of the facts we already talked about. You see that term? Right? If we say an is 1 over n, what do you guys know? That goes to 0 as what? N gets big. Is that right? So your function now, if we say, what is a to the x? Right? And I think where a is positive, right? You guys know what kind of curve that is? That's the exponential growth curve. That curve is continuous. It's really continuous everywhere, right? Over all real numbers, continuous everywhere. So in particular, it's going to be continuous at what number? Right? We're using that first theorem I gave you guys. In particular, it's continuous at 0. Okay, so this is another illustration, not of the squeeze theorem, but of the first one. That function is continuous at 0. I apologize to you guys. There's a typo here. Okay? There's a typo in case you guys haven't seen that. Here's the typo. L. I kept looking at this going, something's bothering me about this. That's why I kept going back at it. It's like, what's bothering me? Because I changed the limit value. There we go. That's what was bothering me. Okay. So that an is continuous at 0, or the function's continuous at 0. So now what we can say is this. We can say that a to the 1n goes to a to the what? 0. And what is a to the 0, by the way? That means this goes to 1. A to the n converges to 1. Because a to the 0 is 1. So I'm just using, again, the fact that we're talking about the continuous, what? Exponential curve. Because this portion, 1 over n, the power goes to 0. And so you show that it equals 1 here. This is what they want you to show. And you did. Okay, you guys okay with that one? That's the substitution principle that they used in Calculus 1. It's called like direct sub, you know. And then give you guys some more examples here. Another example. Using some of these ideas, you got 4n plus 1 over n plus 1. Okay, so they're really looking at this particular sequence here. And they want to know, does it converge or diverge, right? So another illustration of that direct substitution that we were looking at here, I would say, okay, look at this term here. This is your an now. Okay. So where does this go? as n gets big. You guys know? Where would that go? Do you guys know? That goes to what? 4. So you can actually use calculus 1 or calculus 2. You could even use Laplace's rule, right? You can even say, oh, can I look at the limit? Let me get out my purple. So you can use calculus 1 or calculus 2. Right? You say, can I look at this as 4x plus 1 over that x plus 1 as x gets big? And you go, oh, it's infinity over infinity, and then by L'Hopital's rule. So you can use either calculus 1 or calculus 2. That's 4 over 1, which is going to be 4 now because 4 over 1 is a constant. You know. So, and then you might say, well, what does that have to do with that direct sub? So if you want, let's call that direct substitution. Let's give it a name because that's exactly what they called continuity before they called it continuity. So say that's the direct sub principle. You know, using properties that we discussed yesterday. Okay, so now you're going to cite continuity. You're going to say, well, the square root function, right, this is continuous over the interval from 0 to infinity. Okay, so that's a nice continuous function. So you can now say that means take the square root, because this is your function's nice and continuous. That square root function, this is a continuous function they're talking about. Right? In the question. And the square root of 4, you know, is what? Equals 2. And that means it converges. All right, you guys okay with that one? So that's kind of another illustration of direct sub for some of these here. So you look at some of your sequence homework. And then I'm going to give you guys a very important fact here. So let me write this down. The sequence R to the N. I'm going to write it down the way the book does. That sequence is convergent. Okay, if R is between -1 and +1. Okay? So I'm going to give you guys a few notes here for what that statement actually kind of means. That statement means it's divergent for all other values of R. Okay? And in fact, they say, in fact here, the limit of Rn, it equals two things. It's one, which is finite, if R equals 1, and it is 0, for the values between -1 and +1. Okay? So, essentially, here's what I want you guys to really consider here. Okay? So here's kind of what this really is. This is how the book describes it. I describe it differently, but I want you guys to notice this here. This is kind of based on exponential growth and exponential decay. So I want you guys to just consider that curve y equals b to the x. Right? Remember that function is defined to be a positive base, and your base can't be 1. So I'm going to lay the groundwork here for you guys on this. So here's your x, here's your y. That's b to the x. And this is b to the x. Okay, but your base here is bigger than 1, and then your base over here is what? Between 0 and 1. Okay, do you guys remember that stuff? Exponential growth, exponential decay? Those two curves? Okay, so I want you guys to notice a few things here. Let's note. The limit as x goes to infinity of b to the x is infinity for b, for the base being bigger than 1. Is that true? And the limit of b to the x equals 0. And that's if your base is between what? 0 and 1. So we had two situations. Exponential growth, right in here. There's your b. And you had exponential decay over here. Same b. And x, like I said, x is any real number. So now if you said to me, well, what happens if you change your domain to natural numbers, right? So you might say, what does that mean? Well, the limit of b to the n will be infinity, as n goes to infinity, for your base being bigger than 1. Right? Because we're changing the domain from real numbers to natural numbers. That means you have divergence. And similarly, just to kind of do some notes here, this is what this is based on. B to the n equals 0. And that's going to be when your base is what? Between 0 and 1. Okay, just kind of looking at, and that means convergence. Just looking at that curve, that's kind of the key to the statement they're trying to prove to you. You know, it's kind of the key here, although there's more to this proof here. Okay. All right, so now here's what I kind of want to say to you guys. Let's get back to the real juice of this statement here, okay? Let's say this. If the absolute value of r is smaller than 1, then the limit as n gets big for r to the n is 0. Okay, so remember what this is also kind of saying here. Okay, so in other words, also here, 0 is smaller than the absolute value of r. R can't be 0, right? So what we know is the absolute value is between 0 and 1 there. Then we can say that the limit as n goes to infinity in absolute value of r to the n will equal the limit absolute value of r to the n, which is also 0. So really what they're saying to you, what you want to kind of think about this is the following. For that limit, we got this equal to 0 here. Which means, in other words, the limit of r to the n equals 0. Because you showed an absolute value. This was from yesterday's proof. And so let's double check something here. Yep. And that statement here, by the way, is the same as saying what? Let's put that in red. This is the definition here of what? -1 less than r less than 1. So we're essentially showing you that for these values of r, limit is 0. Okay. Now you might say, what about when r is 1? Well, when r is 1, so here's my first case. Well, let's do it this way. If r is now 1, you're talking about r to the n being 1 to the n, which is the constant sequence of 1. And that converges to 1. So now the limit of r to the n is 1 as n goes to infinity. So this is thinking of this as a first case and this as a second case. Yeah. Projector went off? Oh, there it goes back on. Oh, what happened? The audio is still, audio is fine. Oh, what's that? Oh, okay. I'm sorry. I don't know what happened. Looks like here, went off. So let's highlight this. So all we're saying, ladies and gentlemen, here in this, if r is 1, we show that r to the n is going to be 1. And if r is between -1 and +1 for that particular sequence, then that equals 0. And so this is kind of really all we care about. So that's kind of a fact in our book here that we looked at, I guess, that we look at. Okay, so just give you guys that nice fact. That's going to show up later on down the road. So we'll see that down the road, this fact. Anyway, okay. So what do we have now? I think we're going to talk about a few important definitions and ideas here. Okay, so remember something like this here. I want to kind of start to say a few things here. Let me draw a picture for you guys here. Okay, if this was a function, what would you say about this function? Right? Let me do this here. Remember functions, if that was some function f that's nice and continuous, right? If I say to you guys, what does this kind of look like to you here? I'll give you guys some definitions here. Okay? What do you guys remember from Calculus 1? Doesn't we say f is increasing here? So you have what's called an increasing function. Do you guys remember that? That's an increasing function. So I'm going to give you guys a couple of definitions here. Okay? So definition here now, we can say the sequence now, an, right? N is 1 to infinity, is increasing. Okay, this is an increasing sequence. What do you guys know about these terms? This is A1, this is A2, A3, A4, A5. Aren't they getting bigger? So you have this increasing sequence. That's happening if A1 is less than A2, which is less than A3, and then we can put less than or equal, okay? Which is less than or equal to AN, and that's true for all n. If you have this, we can say that the sequence is what? Increasing. So that's an increasing sequence. Go back to the idea of an increasing function. Okay, all the terms are getting bigger. Right? Remember, our domain goes from x to n. That's why we have the dots. So this is an increasing function, and you have now the definition of an increasing sequence. Similarly, you also have what? Decreasing. So this here is a decreasing function, right? So f is decreasing. Remember that picture? Well, you have a decreasing sequence as well. Okay, so this is going to be, this is now A1, the first term. This is A2, A3, A4, A5. And so the terms are getting smaller now. So this is what we say. The definition, the sequence, AN, for n is 1 to infinity, is is decreasing. Okay. If now the following is happening. A1 is less than or equal to A2. I'm sorry, greater than. If all the prior terms are bigger. I'll move this over here. All the prior terms need to be bigger. And that's for all n. So this is a definition of a decreasing sequence. Okay, the sequence is decreasing. In fact, we can write it, generally speaking, in terms of an, just to kind of let you guys know. That for increasing, let me double check. Yeah. Increasing, sometimes we say an is less than or equal to an plus 1 for all n. That means the prior term is smaller than the what? Next term. That's why they say an and an plus 1. So this, you can see in a definition as well, of an increasing sequence. That means the next term is bigger than the prior term. An plus 1 is bigger, notice, than an. And over here, you can say that the prior term is larger than the next term for all n. So you can see this in the definition of what? A decreasing sequence. Okay, so sequences can be decreasing. Sequences can be increasing. Kind of interesting. Okay. Now, I'm going to give you guys another idea, give you guys a couple of definitions here. I'm going to change the color. Maybe not. Let me keep it blue. So here's what we're going to say. Definition. We say a sequence an, okay, is bounded above. Bounded above. Okay, what does that mean? If there is a constant number m, capital M, such that every term is smaller than that, less than or equal to m for all n. Okay? This is what we call being bounded above, and it's bounded above by the constant big M. It's bounded above by what? Some number. So every term of the sequence needs to be smaller than that number. Then we say bounded above, ladies and gentlemen. So I'll give you guys a couple of definitions here on this. Then you go, okay, we've got another definition. We say a sequence is, now we'll have to define the sequence for you guys. A sequence an, again, where n goes from 1 to infinity, is bounded below by little m. Bounded below. This is a different constant. If an is at least that constant for all n. So you got another constant. Maybe I should just change numbers or colors here. Okay, I'm going to change colors actually, sorry. So bounded below by some constant m. This is what it means to be bounded below. I'm going to change this one to orange. And bounded above. Now, this is kind of important. This is important to say for all n. This is something, a detail that people tend to overlook. Right? For every subscript. to give you guys this definition. Okay. We say a sequence, just simply an, for n is 1 to infinity, is simply bounded. Okay. If it's bounded above or bounded below. So you're just saying that it's bounded. So bounded above, ladies and gentlemen. I think that was orange, and bounded below. It's in green. So to just say the phrase being bounded, you have a bounded sequence, it's either above or below. Now, let me draw you guys a quick picture for this here so you guys can see what I'm saying here. See if you guys can figure out what is which. So here's a quick picture. 1, 2. So if you start here, 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 and here. So on. Okay. What is this a picture of? What do you guys think this is a picture of? What letter do I use? This is a picture of a sequence that is what? Bounded above or bounded below? Right? 5, 6, and so on. What do you guys think this is a picture of? Bounded above or bounded below? Yep. Outstanding. If I could get the marker. So this is big M. This is being bounded above. Because every term is below what? That value M. Is that right? That's what they want to kind of illustrate to you. Every term is below that special what? Line. So every term, this is called a sequence that's bounded above. Now you might say, what is the other one's going to be bounded below? What does that look like? Well, we'll show you guys what that looks like as a picture. So if you start here now at 1, and then you're going to do what? Something like this, maybe. 3, 4, and so on. Okay? Now, what can we say? Let's use this here. Now you have another special line. And I'm going to do this. Okay? I'm going to do it this way. Now this is little m. Because this is what it means to be bounded what? Below. Because remember, this is going to be your first term. There's A1, there's A2, A3, and so on. And like this is A1, A2, A3, and I think it was a different color. Bounded above was orange. Sorry. Bounded below was green. Okay, so this is just the definitions of being bounded above and bounded below. Now you might say, Mr. Judge, why do we care about these definitions? I'm going to give you guys a very, very important idea. give you one last definition. I forgot to give you. Definition. We say a sequence is monotone, one tone. Doesn't even have a sound, but okay. Monotone if the sequence is either increasing or decreasing. Okay? So this is the definition of being what we call monotone, one tone. Mono meaning one tone. It has to either be increasing or decreasing. We could say it's just monotone. Okay? Now, here's the reason I bring it up. There's something very special about bounded monotone sequences. And we're going to see that not today, but we'll see that next time. Okay? There's something very special about bounded monotone sequences. And, you know, we kind of focus on those. Does anybody happen to know what that is? What's so special about bounded monotone sequences? Guess we'll stay tuned until next time and we'll find out. Next time being when? Tomorrow, ladies and gentlemen. So take care, stay safe. I do have your homework already in Canvas. We'll see you guys tomorrow. We'll continue with this idea and take care and stay safe. All right, let's clean up some loose ends where we left off. I wanted to kind of share with you guys the very, very famous bounded monotone sequence theorem. Okay, a bounded monotone sequence theorem. And so this is what this is. Okay, and I'll draw a picture. We'll look at some nice pictures and some graphs today. But here's the statement. Every bounded monotone sequence converges. All right, every bounded monotone sequence converges. So I think we have to underline a few things. Being bounded and being monotone. So this is what that means. You got some sequence, AN. So just to kind of go through this statement with you guys and show you guys some nice pictures on it, it's really particular. I think you have to notate a few things here. So in other words, AN goes to L as N goes to infinity. This is what they're saying. But AN needs to be, satisfies two things here. It needs to be monotone and it needs to be bounded. So let's be careful about what this means here, okay? Note. What does monotone mean? Right? We gave you guys that definition yesterday. Monotone means you're doing what? The sequence is either increasing or decreasing. So to tear apart, or not tear apart, to dive deep in what this means. So if you have AN needs to be increasing, and when they say being bounded, they really mean if it's increasing, it has to be bounded above. Okay, you guys okay with that? If it's increasing, it really needs to be bounded above in order to have convergence. So that's my first situation. It has to be increasing and bounded above. Now you might say, why? And we'll see some nice pictures. I found some. Not pictures, but animation. So remember, what does that mean to be increasing? Increasing in general looks like this. This is increasing. Okay, like a to the n equals n. That's an increasing sequence. But it's not enough under the bounded monotone sequence theorem. It needs to be bounded above as well. Being increasing alone is not good enough. Right? You guys know what I'm saying? You say, well, why is that? Because just increasing means that goes on forever. You can't define that epsilon neighborhood. But what does that mean? This is decreasing. But what does it also mean to now be bounded above? This is what it looks like, okay? So you can say this is increasing. However, what's the story? If I do it this way. So this is an increasing sequence, and notice, I'll do this in pink. I could create, I'm going to do it this way. This is kind of like saying you got that L value. But I can create a neighborhood, an epsilon neighborhood around L, where every term eventually will be inside that neighborhood, okay? So this is what they really want to say. If you have an increasing sequence, but it's also bounded above, not bounded below, bounded above, then you can have convergence. And that's what this theorem really means. Okay, because being monotone means either increasing or decreasing. Okay? Now, the other situation, you say because there's two, right? This is the first situation. Well, what if you have the opposite? AN is decreasing, right? Well, then it needs to be bounded below. So if you're decreasing and bounded below now, ladies and gentlemen, you might say, what's the story here? Well, just being decreasing is not enough. Okay? So you're going to have this value as well. It's going to be bounded below. It doesn't have to be the limit value. It could be any number. So like the definition, they use that m and little m that I gave you guys. So just being decreasing by itself is not enough either. So really, eventually, as you guys know, every term of that sequence needs to be in that neighborhood, right? So this is what it means. You got to be decreasing, but also bounded below specifically. This is that first term. If you guys remember, this is like A1. This is A2. This is A3. And then over here, this was the A1, A2, A3. So essentially, this is what the theorem is saying. You got to be monotone, strictly decreasing or increasing. But it also has to be the appropriate boundedness, either below or above. And if you have that, you'll have your convergence. You got this thing. That's the theorem. Now, the book proves it for you guys. I won't prove it to you. There is a course called Advanced Calculus where they focus on all the proofs, and you prove some of these things too. But anyway, we're going to kind of look at some pictures today, or some animation today, because in your book, there are some homework questions, and I didn't bring it with me. I'm just curious, does anybody bring their book with them? Okay. Anyway, I'll have to change and modify your homework, but The book says something like this for some questions. They want you to graph the sequence to determine if it is convergent or divergent. So generally we write that sequence as AN. So, okay, we'll look at a nice example, like one of these examples. Now, I just want you to point out to you guys that some of these here, they just want you to graph. Two plus negative 2 over pi to the nth power, that kind of sequence. So I'm going to go to Desmos, ladies and gentlemen. And in fact, more than that, I have it online here. Now, this particular sequence here is a different sequence. I want you guys to note something here. Let's do a note here first. They have AN is negative 8 over 9 to the nth power. Okay? So I'm going to do a note to share with you guys what Desmos has there automatically. So does this sequence converge or diverge, right? What do you guys know? Well, yeah, remember that theorem I gave you guys yesterday? We proved this here. Where was it? Somewhere. All right, let's go back over here. Let's look at this theorem here. If R is between -1 and +1, then what is that limit? That limit goes to 0. Is that true? Well, let's look at some details, first of all. Is it that theorem? Yeah. So in that theorem, my R is -8 over 9. So if you have R between -1 and +1, meaning really if the absolute value is smaller than 1, then we know R to the n goes to 0. Is that true? This is what we proved yesterday. So here's that R value. So just to illustrate some of these ideas we did yesterday, you go, oh, that's kind of interesting. So this thing converges to 0. I want to also say something to you guys here. This is one approach. The other approach is if we say, remember this? The absolute value of AN is the absolute value of -8 over 9 to the nth power. Is that right? Absolute value of -8 over 9 to the nth power. And this is going to be what? +8 over 9. That goes to 0 as n goes to infinity, right? So what that meant before we seen this, that means a to the n goes to 0 as n goes to infinity, because we showed that the absolute value of a to the n goes to 0. So remember, if you can show this, then we know a to the n goes to 0. And that's what we just did there. Okay? Anyway, there was two ways to do it, is what I'm saying. There was two ways. Now, let's look at the graphic, right? Because in Desmos, they're showing you graphically now. Oh, where's my... Let's get rid of this. I wonder if I can... See this here? This is that same sequence. It's alternating, plus and minus. Alternating. But it's alternating around 0. So to some degree, if you wanted, I know. Just going to kind of do this here. You guys already know I don't like putting red in, but I just did. Come on. Okay, so I want to share with you guys again that what? Around 0, we have that tunnel, that epsilon neighborhood, where eventually every term of the sequence is around 0. And it doesn't matter how the width of my epsilon. It could be, this is true for any epsilon. Remember that? That around 0, you created that epsilon neighborhood. That L minus theta epsilon, L plus epsilon interval. That's what convergence means. Anyway, so I kind of share with you guys that particular sequence. Let's go back to this one here. Because the book is just kind of saying to you guys, hey, graph this. I would say use Desmos if you wanted to see that. Let's see what this one looks like. 2 plus, this is alternating, but it's going to be interesting here, okay? So I'm going to change this here, see if I can. I think I can. So let me change it. That's now going to be 2 plus, oops. That's weird. It doesn't like me doing 2. There we go. 2 divided by pi. Okay, you guys see this one here now? You go, Mr. Judge, that's around 2. That's a picture of what again? Right? You see the terms of this? Start at n as 1. It's alternating around 2, isn't it? So what do you think that looks like? Can I draw that epsilon neighborhood now? Looks like I can around 2. Is that right? So for any epsilon around 2, ladies and gentlemen, what's the story here? I can create a neighborhood around that 2 where eventually every term of the sequence is in that neighborhood. Right? It's around 2 here. This is the L plus epsilon, L minus epsilon. That's good for any epsilon. However small I make it, eventually every term of that sequence will be there. So this converges around 2. Does anybody know, how can I show that? How can I show that if they said, show that this converges? Now, this is just looking at this graphically, but how do you think we can show something like that? Do you guys know? Well, what's the limit of an? Isn't that 2 plus what? Negative 2 over pi to the nth power? What are the properties of limits? Is that right? So where does this limit here around 2 go to? Where is this one going to? Where does this go to? Why does that go to 0? Right? Isn't that my R value that we talked about yesterday? So if R, if that base is negative 2 over pi, do you guys know what pi is? It's about 3, is that right? So what I'm saying is the absolute value of R is smaller than 1. So that means that that limit is going to be 0 here. Okay, that was the same fact I proved yesterday. You guys remember that? So that means this limit equals what? 2. So by properties of limits, that makes some sense. So you have the graphical approach. That's kind of what they want you to see. So I just wanted to point that one out to you guys. And then, just to kind of look at this graphically as well, sin n over the square root of n. Because they want us to kind of look at that graphically. Wonder what that one looks like. Oops. Sin n. You go, whoa, is that what that looks like? Well, sort of. See this in terms of the sequence? Does it go on further? I might be able to change that. N equals 100. I don't know if I want to mess with that. Anyway, what do you guys think is happening? Can I put another 0 there, please? Darn. There we go. N equals 1,000. What do you guys think? Anybody see what's happening? What should happen? Yeah, that's around 0. Is that true? So let me remind you guys a little something. How can I show that like I did yesterday? Right? What do you think that would? How do you show this as 0? How do I know this thing goes to 0 as n gets big? Right? Because we just seeing the picture. I'm not going to bring in the graphic. I guess I could. I kind of want to. But yeah, it's by squeeze theorem. Okay, so it's by squeeze theorem. And let me do something like this if I can. Who never knows? Maybe one day my videos will go viral and I'll make $1 billion. And what do you guys think? I don't know if anybody cares about math videos, in all honesty. Where'd it go? Oh. No, I think I created a new note by accident. I did. Okay. Let's create that epsilon neighborhood around what? Around 0. Eventually, every term is going to belong to that what? Epsilon neighborhood around 0. For any epsilon. Now, you said, Mr. Judge, how do we show this? We did it yesterday. So by squeeze theorem yesterday, remember this, the sign is always between -1 and +1. Is that right? And then if you go now and divide the middle by the square root of n, the right by the square root of n, the left by the square root of n, that number is positive. It doesn't change the direction of your inequality sign. So now the limit of 1 over the square root of n is equal to the limit of -1 over the square root of n. They both equal 0. So I'm sharing with you guys what we did yesterday. That limit, the smaller limit, is 0. And then the upper limit is also what? 0. And that forces the limit of the middle to also be 0. Say this is the limit as n gets big of sine square root of n over n equals 0. And you must say by what? By the squeeze theorem. And that's what you use here. This is an illustration of the squeeze theorem. Anyway. All right. So, you know, we do have some nice kind of pictures of some of these things here, just so you guys know. Okay. So now they might say determine whether the sequence is increasing, decreasing, or neither. Neither means non-monotone. It's not monotone. Okay, so I just want to share with you guys a picture of this so you guys can see something like that, right? So what do you guys think? Oh, it's not there. Over here. So that's 1 over where did it go? There we go. There it is. Yes.
So monotone, we can say that it's not finite, right? So when you say
No. It is simply the following. You are either increasing, decreasing. Being monotone means it's either increasing or decreasing. So what would you say just by looking at this picture? The terms of the sequence are what? Increasing or decreasing? They're decreasing? They're getting close to 0? Well, they're decreasing. I think I don't know if it can do the no, where is it? See, this is in decimals on the website, and I want to adjust. I guess that doesn't let me adjust the width of this. So this is a very classic question of a decreasing sequence. What does that mean to be decreasing? A1 is bigger than A2, which is bigger than A3, and so on. Okay, you guys okay with that? In other words, AN is bigger than AN plus 1. And that's true for all n. Okay? But how do we know this? We looked at it graphically, but how do you guys think we can show this? Well, what is AN plus 1 by definition? That's 1 over 5n plus 1. Is that right? So what I'd have to show, as this is true for all n, right? How do we know this? Well, yeah. I mean, you can also you could do it that way too. You can say, if you took that criteria, I mean, we're trying to show that 1/5 to the n is bigger than 1 over 5th to the n plus 1. How do we know that that's true? Right? So let me share with you guys. This is what we're trying to show. If we can show this, and this is for all n, we know this is a decreasing sequence. So sometimes I think it's good to say this is 5 to the n versus 5 to the n plus 1. Okay, which is bigger? Yeah. Well, no, we have to strictly show it satisfies this definition. There's 2 ways we can do it. You might be right, but that's not showing. I mean, it's like you can even say, like, if you notice this, f of x, this is the same as 1/5. Well, isn't that a decreasing exponential function? So this is decreasing. Because fn, this is the same exact sequence. So it's decreasing. We know that. But if they want you to strictly show it, this is what I'm saying to you guys. This is a proof-oriented kind of idea. One way you can do that is to say, which one of these is bigger? Is 5 to the n bigger or 5 to the n plus 1 bigger for all n? Which one's bigger? Isn't that true? That's for all n. Okay, are you guys with me on that idea? Because you say, why? Because this is 5 to the n times what? 5. So it's actually 5 times bigger, I guess. Is that right? You guys with me on that? By properties of algebra. Now, what you use here, this is something you may not know. And this is something I learned in this class. Here's a fact. Okay? Bless you. If A is smaller than B, where both A is positive and B is positive, okay? Then you guys want to know something? Then 1 over B is less than 1 over A. So what I want to share with you guys is some of these ideas here. This is gold here. Now, I can actually prove this because, if you assume A is smaller than B, but you must have positive numbers, okay? Then algebraically speaking, I can divide both sides by B. Now, since B is positive, it doesn't change the inequality sign. Is that right? That's why you need positive numbers. So now you say, oh, is AB smaller than 1? Yeah. I can now divide both sides by A. A is positive. It doesn't change the direction. So you say, is that AB divided by A is less than 1 over A? And that's A over B times 1 over A is less than 1 over A. So what do you get? You get the relationship that 1 over B is smaller than 1 over A. So what I'm saying to you guys is this statement I just showed you guys is really behind this proof. See, they don't share with you guys this. This is proof. You guys know sometimes students say to me, Mr. Judge, should I take that linear algebra course when? You know what I mean? Why is linear algebra hard or harder than differential equations? Because it's more proof-oriented. So some of these math courses, as you move on, are proof-oriented. And what you guys are looking at is kind of the start of that. So, you do have these proofs. So we start with this statement, and I can now say 1 over 5 to the n plus 1 power is smaller than 1 over 5 to the n. By using this statement I just shared with you guys. Now, what is this statement? Well, that statement is what? That's a to the m plus 1 is smaller than a to the n. Because that's the definition. And go back, what does that even mean? Well, if I write it as a to the n first, isn't that our definition of what? That's our definition, ladies and gentlemen, of being what? Increasing. Because the definition is right here, or decreasing, sorry. So that we just showed that this sequence is decreasing just by looking at the definition here. And that's kind of important to do. So you go, what does that mean? Well, means it's a strictly decreasing sequence because we showed it satisfied this definition for all n. And really, it starts right in here. It starts with this statement. So it's really a 2-line proof. But you're never going to know the second line if you never knew this fact. And knowing this fact does require a proof. And this is the proof for it. This is just thinking of numbers, though. But you do need these numbers to be strictly positive. If you don't have that, you can't say it. And it doesn't change your inequality by doing the algebra. So that's kind of an important detail that people don't share with you guys sometimes. But it's a powerful tool, you know. So we know that sequence is, this is what it means to be decreasing. But we knew already. Decreasing sequence. Moreover, this is bounded below as well. So I'm going to say also, an, which is 1/5 to the end, is what? Bounded below. What does that mean to be bounded below? Do you guys know what it means to be bounded below? Being bounded below means there's a number smaller than that sequence for all n. There's a lot of numbers smaller than that. I can say this to you guys. An, that sequence is bigger, is greater than or equal to, I'll say maybe -2. It doesn't matter. This was that little m value for all n. How do you guys know this is bounded below by a lot of numbers? It's bounded below. How do we know? Because 1/5 to the n, isn't that strictly positive for all n? Isn't all the terms bigger than 0? So you can have any number for that little m. So what you can conclude is that this sequence is decreasing, and it is bounded what? Below. Therefore, it is what? It's convergent. Okay? It's convergent. They didn't ask you to prove that it converges to 0. You know, they're just really asking you, is it increasing, decreasing, or non-monotone? Non-monotone means it's neither. You know, do the same thing for the next question here. Like you have 2n minus 3 over 3n plus 4. Now, this is going to be more complicated. I would not use the arguments for the definition here. Okay, so we want to know, is this particular sequence increasing or decreasing? So there is a simpler way to do some of this without, you said, Mr. Judge, how can I do this without doing your fancy number logic and using the definition? Right? How can we do that fancier? Not fancier, I'm sorry, in a more simple way. Remember what this is? This is Fn. Do you know what you guys can do? Take a look at the function 2 to the x minus 3 over what? 3 to the x plus 4. Let me share with you guys where I'm going with this. Okay? Now, I can go to Desmos. I'm not going to go to the sequence version, but I'm going to go to this regular y equals, what is that? 2x minus 3. Okay? Divided by, and then I guess I have to do a parentheses. 2x minus 3. Divided by 3x plus 4. Okay? So here's the curve. This isn't even a sequence version. But what do you guys think about this function? What do you guys know about this? Isn't it increasing over that interval from 1 to infinity? Right? And if you said, no, I want to see that in the other Desmos here. All right, I'll go back here then. Parentheses. 2, well, not 2x, 2 what? N. 2n minus 3. And then 3n plus 4. Okay. What do you guys think? What does this mean? What does that look like to you? I'm going to say that looks increasing. Is that true? Isn't that an increasing picture? And it also bounded above. That's true. But the point is, the question they're saying is that increasing? And the answer is, yeah, that's increasing. And it is also bounded what? Bounded above, which is going to say that it's going to what? Be convergent. Okay, so here's the picture, just to let you guys know. This is kind of what you're dealing with. But how can I show that this is an increasing sequence? Because it is. I mean, the graph is showing it. You guys see that there? And it is bounded above, and so it's going to be convergent. But I want you guys to do this. Go back to Calculus 1. Yes, what do? Sign analysis on what? On the derivative. Oh, man, are you serious? Yeah. So to let you guys know, oh, I guess it was in purple. You might say, Mr. Judge, do I still got to do derivatives? Oh, yes. So, quotient rule, is that right? What's quotient rule here? Isn't that 3x plus 4 squared times what? 3x plus 4 times, what's times 2, is that right? Minus 2x minus 3 times 3. Isn't that what it is by quotient rule? Which is 6x plus 8 minus 4x minus 9, everything over what? 6 plus 4 squared, double check. Six x plus 8 minus, that's 6x minus 9. Yeah, I thought something was wrong. That's really minus 6x plus 9 over what? 6 plus 4 squared. And then you say, what is this? It looks like it's 17 over what? So there's my derivative. So by sign analysis, you guys remember this by sign analysis? When x is negative 4/3, that derivative is undefined. Okay, this is on that derivative here, sign analysis. Now give me a number to the right. Oh, 0 is a nice test point. Number -2, nice test point. So I plug in 0, don't I get positive values here, ladies and gentlemen? That's an increasing function. If I plug in, what's the deal, -2, I also get what? Positive values. So here's the thing. F is increasing on the interval negative infinity up to negative 4/3 union negative 4/3 up to infinity. So if I was taking calculus 1, you go, okay, yeah, that's the nice stuff we did in calculus 1. Now, why is it that a lot of this curve is missing? Because we changed the domain. Is that right? Our domain is natural numbers. It's not real numbers. That's an n. Those are natural numbers. So what is n? 1, 2, 3, and so on. Is that true? So that means what we just showed is this, because where's your natural numbers? Over here, 1, 2, and 3. Is that right? If we just look at the natural numbers, ladies and gentlemen. So what you're really showing here is simply this. That AN is what? Is increasing. AN's increasing because the function f of x is increasing on that interval. If I can find this color, right? Because f of x is what? Increasing over the interval negative, 4/3 to infinity. That's an open interval. So you're showing calculus 1, ladies and gentlemen, to show that this thing is increasing. Now, is it bounded above? It is. So they didn't ask you, they just said, oh, is that increasing or is it decreasing? This was increasing, but I want you guys to know that it's bounded how? Above. So being bounded above means AN is less than or equal to some big N for all N. And my AN, you go, what is this? 2n minus 3 over what? 3n plus 4. This is my AN, okay? Now, this is what we're going to learn, ladies and gentlemen, is this. Okay? M is some constant. Remember that? Some constant, some M. So I just want to share with you guys, this is bounded above. This is the idea. So, you know what happens here, right? I'm going to share with you guys. It is equal. This is equal. But if I make my numerator, you see this negative 3, right? What if I get rid of that negative 3? What happens to the fraction if I get rid of that negative 3? Does it get larger or does it get smaller? The whole fraction. So if the numerator is what? Which one's smaller? Which one's larger? Isn't the left smaller than the right? Is that true for all n? So we're focusing on the numerators here. So all I'm saying is I'm going to get rid of that. And then what happens down here? We said, let's focus on the denominator now. Well, guess what, ladies and gentlemen? If I get rid of the denominator, now I'm going to say this. Isn't this thing bigger than 3n in the denominator? So if I get rid of that, I get 2n over 3n. Because this means 1 over 3n is greater than 1 over 3n plus 4. Yeah. And this cancels here. So here's what I want you guys to understand, that what you're looking at here is that an is in fact smaller than what? 2/3. So this is what we just showed. An is smaller than 2/3. Now, this kind of logic, ladies and gentlemen, comparing numbers and fractions, is really behind this idea of, in general, by definition, increasing, decreasing, and even by being bounded. So we know that this thing is bounded. Now, you might say, okay, it's nice that we know this is increasing forever, but it's also bounded above. So bounded above, that's what this is showing. An is what? Bounded above. What's the conclusion, by the way? The sequence an is what? Convergent by the monotone bounded sequence theorem. This is a very famous theorem, ladies and gentlemen, from this section. Very famous theorem. Bounded monotone sequences converge. Yeah.
How could it, by doing, graphing, how could we know it's bounded above?
Well, okay, good question. How do we know by graphing it's bounded above? This is increasing, right? And it's let me share with you guys another part of this. So just so you guys know. We know it's bounded above. Here's a direct answer, because we proved it's bounded above right here. An is smaller than 2/3. So that's how I know it's bounded above. That's the direct answer. I want you guys to also notice something here, right? They didn't ask you this question here. But if this was yesterday, because today we're talking about that theorem. Yesterday, they might have said to you guys, as an example, they might have said, show that the sequence 2n minus 3 over 3n plus 4 is convergent, right? And then you might have said to me, how do I do that? Well, you take the what? The limit. And what is this limit going to be? It's 2/3, isn't it? Isn't 2/3 finite? You see what I'm saying? Now, how else could I have done this? I could have went to Calculus 1, and this is kind of what we're talking about yesterday, right? Calculus 1 and Calculus 2 shows that this is 2/3. Okay? Calculus 2 has you use L'Hopital's rule. Right? Did you do L'Hopital's rule some of these? Remember, this is a vertical asymptote in Calculus 1. Right? So VA is a vertical asymptote from Calculus 1, because that's finite. So you say that happens, your vertical asymptote happens at x equals what? 2/3. Now, there's no coincidence that if I told you here, and you guys already know, I don't like red for my graphs, but if I said to you guys, y equals 2 divided by 3, just to kind of do this for you guys, right? I like doing asymptotes with that line here. Okay. When the book says things like, can you graph this and show, this is, in other words, this is the real numbered graph that demonstrates two concepts from Calculus 1. What's the first concept? the function's increasing over that interval from 1 to infinity. It's really negative 4/3 to infinity. Is that right? We did sign analysis on the first derivative. What is the limit? Vertical asymptote. That limit of 2/3 happens to be the upper bound of that function over the interval that you showed by non-calculus ways. Because you take the same curve, this is over real numbers, and then now in Desmos, they call it a sequence because the domain is natural numbers. Yes, that boundedness, I can say the same thing. I would like to get my, don't know what's going on again. Oh, there we go. I guess y equals 2 divided by 3. This is what I just shared with you guys, the bounded constant 2/3. But we use the argument of the relationship between a fraction that 2n minus 3 and 3n plus 4 by removing the constants negative 3 and 4. We just show that that's smaller than 2n over 3n, which is actually 2/3. So you're looking at a couple of things. Calculus 1, and then now using the definition of increasing and also being bounded above. And that's really what the theorem is. Every bounded monotone sequence converges, meaning you can't just increase. It has to also be bounded above. So if you're bounded above and you're increasing, it's convergent. And that's the thing. It doesn't tell you the limit, but it tells you it's convergent. So, we're just going back a little bit and showing you guys with the definitions I gave you yesterday, the power of that particular theorem. Because chapter 12:1, for some people, they believe that's the theorem of the chapter. Bounded monotone sequences converge. They don't tell you what it converges to. They just tell you that it converges. And that's the illustration of today, in all honesty. This is what I wanted to talk about. Yes, question? No. Monotone means what? Your sequence is either increasing, getting bigger, the terms are getting bigger, or the sequence is decreasing, terms are getting smaller. That's what it means to say it's monotone, one tone. Mono means one. So in terms of sequences, they call it monotone. You mean you're strictly doing one thing. It's not going up and then going down. It's strictly going up or going down. But they use the phrase monotone. And then you say, what about the other phrase, non-monotone? Well, the other phrase, non-monotone, if I do something like this, let me try this out. I'm not sure if this is. Let's change this to n plus 1 divided by n. Okay? Oh, look at that. I'm going to get rid of this thing. What do you guys know about that sequence? This is n plus 1 over n. Is that sequence monotone? I would say yes. How do I know this is monotone? It's strictly increasing. But is it bounded? Is it bounded above? No. What does that mean? It's divergent. So just because it has to satisfy two things, it has to be increasing, that means it's monotone. But if it's not bounded above, you can't say it's convergent. Because a strictly increasing sequence that is not bounded above is divergent. This is a picture of it. Now, can I prove it? Yeah, I think so. I don't know. Let's think about this. Can we show that this thing diverges? Right? Well, what does that mean algebraically? Is this n squared over n plus 1 over n? Is that right? So an is really what? n squared plus 1 over n. What's the limit as n gets big of this sequence? What is that? What happens here? Do you guys know? You might say, Mr. Judge, I'm going to have to go to calculus. Calculus 2. Or you don't have to. Oh, infinity over infinity. Okay, use what? L'Hopital's rule. Okay, what's this? 2x over 1. What is this limit? Is that infinity? It's infinity. What does that mean? That means the limit as n gets big of n squared plus 1 over n is also infinity. What does that mean? That means your sequence, since this is an, diverges. So it means an goes to infinity as what? N gets big. That means it's a divergent sequence. So, ladies and gentlemen, we actually knew that. That was the original sequence. But we actually kind of know that by the graphical picture. See what I'm saying? That's going on forever. That's increasing without bound. So it's monotone, but that's not enough to say that it converges. Monotone sequences, right? If it's an increasing sequence, has to be bounded above to converge. And this one's not bounded above. Let me see if I have another one to kind of sneak in here. What do I have? N times E to the minus N. Okay, well, that's you can't see much of this. Oh, I know. I'm thinking. What are you guys thinking about this one? What do you guys know about this sequence now? That's a decreasing sequence. What do you think that means? That's also monotone because strictly decreasing. It's not increasing then decreasing or decreasing then increasing. It's strictly decreasing, so we say that's monotone, one tone. Okay, is it bounded below? Yeah, what do we know? Converges. Because bounded monotone sequences converge. We don't know what it converges to. We can see it here in the picture, though. But how would you show that converges? What do you guys think? Where does that converge to? Right? If they told you an is what? N to the minus n. And they want you to show this what? Converges. What would you do? You need the limit as n goes to infinity of n e to the minus n. What is that? Well, you might say the limit of n over e to the n. Is that true? Just using a little algebra. Does anybody know anything special about this? This goes to 0. How do you know this goes to 0? Okay, maybe you say, Mr. Judge, I don't know that this goes to 0. Go to calculus 2. Oh, infinity over infinity. L'Hopital's rule. Okay, 1 over e to the x. Oh, what is this? Isn't that e to the minus x? So this is a limit as x goes to infinity, e to the minus x. Didn't you guys have a test on those things? Sometimes people say, Mr. Judge, is this test comprehensive? I'll say, yeah, because what happens, sometimes you need L'Hopital's rule. Sometimes you need to look at the limit of e to the minus x. And that equals what? 0. So what that means, if it's True for all real numbers. It is true for when the domain is also natural numbers. So this limit equals what? 0. Now, we knew that by looking at the graph. And again, sometimes, sometimes, ladies and gentlemen, the book will say to you, hey, look at the graph and tell me what you see. And that's what they want you to understand. Do you know your definitions? Do you know what you're looking at? Do you know the fact that just because you have a decreasing sequence doesn't always mean it'll converge? Just because you have an increasing sequence doesn't always mean it will converge. It needs to be bounded. You're really looking at the limit. Right? So what I did was, if you guys want to know, this is bounded by 0. It's bounded by 0. All you got to do is find a number that particular sequence to be bounded below is actually bigger than. It could be you can say -1, -2, -3. You can say any number to be bounded. You show that actually algebraically. Or you could even look at the terms and go, okay, you can say, what are the terms here? So you're talking about being bounded below this particular, n over e to the n, right? Here's what I'm saying. Terms are what? 1 over e, 2 over e squared, 3 over e cubed. I can say to you very simply, I can pick any number. I can say this particular sequence is bigger than like -2. Because all these things are what? All these numbers are what? They're positive, aren't they? Aren't they all positive? So because they're all positive, I can find a lower bound. That's that little n. So this is bounded below. So a decreasing sequence, and you say, how do I know that's decreasing? Use calculus. Use calculus. Take the derivative. You say, how do I know that that's a decreasing sequence? Very easily, take that function x e to the minus x and do sine what? Analysis on that first derivative. Show that it is decreasing over your interval, from 1 to infinity. And so that's how some of those questions are done in the book and the homework. And they go, oh, how do you show that? They use calculus, sine analysis. They go back to calculus 1. So you're really finding in some ways, you're looking at two things. Sine analysis on the first derivative, show that it's, where it's decreasing, increasing. And also, you're taking the limit at infinity. You're finding that vertical asymptote. Anyway. So I wanted to share with you guys the graphical relationship between all these things and the calculus 1 and 2 of it to just give you a more complete demonstration on why that monotone bounded theorem works. Because like I said, for 12.1, some math instructors feel you got to know that as calculus students. Bounded monotone sequences converge. They don't tell you what they converge to, they just tell you that they converge. And the important points are knowing what does it mean to be increasing, decreasing, which is monotone, the general phrase. What does it mean to be bounded below? What does it mean to be bounded above? Anyway. Okay, you guys, your test 3 is due on Monday, and, we'll start 12.2. I'll update your homework for sequences 12.1 so you can look at a few of these. All right, see you guys later.